Exponential equations and graphing of exponential equations are a certain type of equation that you're probably not surprised are going to contain an exponent. And it's not that I'm going to harp on this, but you probably have seen some of this before. Honestly, even in Algebra 1, you may have touched on this. Algebra 2, you should have touched on it. But whether you have or haven't seen it, we're going to understand it this year. I'm just saying that some of it could, as always, look a little familiar. Now, again, exponential equations, they, not surprisingly, have an exponent, but it's the type of exponent that's actually pretty important. It's the type of exponent. We're going to use these two equations as kind of our little sort of intro equations. As you jot them down, we have 5 to the x. We have 5 to the x. And we also have 9 1/3 to the x. 9 1/3 to the x. Now these are two nice little happy exponential equations. They have all kinds of stuff to kind of say to us. But the first thing they say is x is in the exponent. And even though that's kind of simple, that's actually pretty important. Let me say it again, x is in the exponent. And why is it so important? Well, that's a new place for x. It hasn't been there this year. Okay, we've seen x in other places. We've had the sine of x. I hope you don't totally forget about sine and cosine. We've had x that has shown up in, of course, polynomials and all kinds of different graphs, but now we have an x up and an exponent. So what's it going to look like? What I'm going to do is just use my graphing calculator. You don't really need to do anything, but I hope just kind of follow along. You don't need to necessarily do this yourself. You can just watch. But I want you to see kind of what 5 2 to the x, what that looks like and what the numbers do. Here comes the graph, maybe a graph that, again, looks somewhat familiar. Graph 5 to the x. Just so you know, I didn't pull anything funny on you here. I just typed it straight in like it shows. Now, look at the kind of graph you get when you have 5 to the x. And at least this year, this is a new kind of graph. And to put it bluntly, we call it exponential growth. It's called exponential growth. Exponential growth is actually a pretty popular type of model or graph. And as you can probably see, the graph, first of all, is growing. It keeps going up. It goes up in a special way, though. If you'd like to look more closely with me, it's just something you can look at. If I investigate some points on this graph, maybe the Y-intercept is 0, 5. Now, that's interesting. Oh, yeah. If x equals 0, if I put a 0 in here for x, I'm going to get 2 to the 0. Well, we just learned, of course, that equals 1. And 1 times 5, oh, that's why 5, that number in front of the equation, that's why 5 is the Y-intercept. Now, look at some other points with me along here, like maybe the point that goes with 1. It's not random because when I go to 1, I see that the y value is now 10. When I go to 2, I see that the y value is 20. When I go to 3, I see that the y value is 40. Now, how good your memory there in the last 10 seconds? We went from 5 to 10 to 20 to 40. Do you see what's happening with the numbers on this graph? 5 to 10 to 20 to 40. It's a special kind of change. It keeps doubling. Now, actually, you say, well, that's kind of simple. Yeah, it's kind of simple, but it's the kind of change represented by that equation. And it's because the base is 2. Since the base is 2, every number, like Mason said, is doubling. That's the only way that you can get an equation like that. Of course, if I go to 4, I'm off the screen, but my next number is 80. And you see what happens if you start doubling numbers. Well, they get very big very quickly. And that's what students and teachers will typically call exponential growth. because numbers are getting very big very quickly. The number in front is the y-intercept. The base is what allowed this equation to double. It's what allowed it to grow.
So when you say the y-intercept, you're referring to 5.
Yes. Now actually we'll write that down in a moment, but you're welcome to process that now. Let's look at the other equation. We've got a 9 and then a 1/3. I'll just type it in. We've got a 9 and a 1/3 to the x. I need to kind of change the window just a little bit so you guys get the full effect here. Sometimes kids look at that equation and feel like it's similar to the other one. Well, it's similar, but it's actually, in a sense, the opposite. It's actually the, instead of being growth, it's decay. We actually call it exponential decay. And as you can see, the graph is now going down. Maybe some of the same things are true. Well, they are. Like the number 9, it's the y-intercept. Again, if I plug a 0 in for x, I get 1/3 to the 0. That's 1. And then 1 times 9 is 9. So that's why the number in front is the y-intercept. Now the base is 1/3. I wonder what's happening to our numbers. Well, I'm at 9. Look at my next number. Now I'm at 3. Look at my next number. Now I'm at 1. Are you surprised? We went from 9 to 3 to 1. What's my next number going to be? It's going to be 1/3. This is sometimes a little harder for people to see, but every number, what was it again? 9 to 3 to 1, and then even to 1/3. Every number is either being divided by 3 or being multiplied by 1/3. As a student might say, it's being cut in thirds. Now if I go to the next number, what's 1/3 of 1/3? Well, 1/3 of 1/3 is 1/9. What's the next number? What's the next number? Well, it didn't like that. But basically, as I keep going along this graph, I keep cutting numbers into 1/3. What happens if I keep cutting numbers into 1/3? Well, they obviously keep getting smaller and smaller, but they're never going to equal 0. We have an asymptote. And I'll say again, because we just got done talking about asymptotes, but we have an asymptote at 0. That's because, well, this graph will never completely cut itself up to be nothing. Okay. And this is what's always true with exponential decay. Now, there's lots of things in the real world, I'm serious about that, there's lots of things in the real world that follow exponential growth and decay. Now, all exponential equations are going to fit into this model. I'm not talking about somebody that's dressed nicely, although it is a nice equation. This model simply says that whenever you have y equaling a b to the x, whenever you have y equaling a b to the x, well, it's always going to be exponential. And we actually call it the exponential model. And if there ever was an equation that, well, that maybe is dressed nicely, it's this one. So we call it the exponential model. But in all seriousness, that's because all equations of this form are going to be either growth or decay. Now, did you pick up on a couple things from just a quick little intro? The letter A, the number that is in front of the base, we call that starting value. Notice I didn't call the y-intercept. I did that on purpose. I called the starting value, but it does start on the y-axis. That's always going to be true. And then this letter B, as you'll come to realize, it's kind of the, I'd say the most important number because it basically determines if we're going to be growing or decaying. There's a lot in this letter B, but take this in. It's going to be the rate of growth or decay. And if that number B is greater than 1, it's growth. But if that number B is less than 1, it's decay. We'll say more about that. But it's interesting, it boils down to just these two numbers, A and B. Now, what we want to do today is we want to try to graph some equations, and that's normally what the goal is. I will share with you that eventually we'll take this knowledge that you're learning and we'll apply it, okay? You know, when we start doing that, again, just from past experience, kids, they start saying, I get it, or it makes sense. But for now, we're just going to be graphing some simple numbers, honestly, for the sake of trying to get comfortable with this. But soon, will be an application. So if you're an application type student, come back, okay? Because if we write down the equation y equals 2 to the x plus 4, okay, in a couple days, those numbers will actually mean something. Right now, it's just what is the graph of 2 to the x plus 4? I'll share that we're going to try to graph this like without a calculator, like without Desmos. Okay, so even though you could type this into Desmos, let's think about how we could look at these numbers and basically come up with a graph with some knowledge. Okay. Now, this is new, but here we go. By thinking about what is the base. Now, the base is clearly the number 2. It's really the only base that we could choose from if I want to put parentheses around it. But what that's trying to do is help you see that there's a number in front of 2. And a number in front of 2 would have to assume to be the number 1 in this problem. And that's also pretty important because that's the place I'm going to start. Now I'm going to start at the number 1 on the y-axis. I'm going to choose to put that down as like a little star. We'll use a little star to note that starting value. All right, now at least this morning you haven't seen an x plus 4, but over this year you've seen an x plus 4. And I want to remind you that whenever you add to x, again, whenever you add to x, it's always a shift. It's actually a shift to the left. So what I hope you realize is that my starting point, remember, it was started at 0, 1, is going to shift to the left. Now if I shift to the left 4 units, I'm going to actually come to rest at a point that is on this graph. And you'll come to realize that we want to label this point, but you have to do a little bit of counting. And of course, if I shifted to the left 4, and I already started at 1, actually would be at negative 4, 1. Now we'll do more of that, okay? I call that a shift point. We'll do more of that. What I'd like to do now is help you guys see what's known as the Y-intercept. Well, of course, you know what a Y-intercept is. It's always found by plugging a 0 into the equation. Now, when you plug a 0 into the equation for x, you get basically 2 to the 4th power. Well, 2 to the 4th power, we've kind of been studying this, and you already know that it's going to be 16. But that gives us another point on our graph. It's the point 0, 16. Look what's kind of happening here. I know this might be a different way to graph a line, but we're coming up with points. The first point was a shift point. The next point was truly the y-intercept. Okay, there's something else though that goes on this graph. It's an asymptote. Now you heard me, you saw me, I showed it to you on that intro graph, but I want to remind you that there's always an asymptote that starts at 0. So this graph will also have an asymptote at 0, so get it in there, get it labeled, and then draw it with a nice little dashed line. Now the last thing to do, I hope you notice, is to use the only number up here that we haven't discussed, and it's the base. Sometimes kids will kind of wonder, well, what's up with the base? How come you didn't mark it as a point? It's not a point. It's the growth or decay number. And simply because that number is greater than 1, it's going to grow. It's going to be growth. Don't overuse the base, although it's a really important number. Don't overuse it. It's not a point. It's actually just the shape of the graph. Now, because it's a growth graph, you can trust me that it's going to look like all other growth graphs. And so when we connect the dots, we connect it with exponential growth. And exponential growth is going to grow quickly. It's also going to taper off and get close to this asymptote. What I just took you through is what I typically call transformations. Transformations are when we try to think about shifting, when we try to think about the Y-intercept, and then also the asymptote. If that kind of list of items helps you, feel free to jot it down. We're going to do it though a few more times. So we're going to use transformations. We're going to try to come up with these shifted points. We're going to try to come up with the new Y-intercept. And I got some good news about the asymptote. Everybody gets the asymptote right. Okay, now, this definitely is loaded. We've got 2 1/2 x minus 2 plus 3. Let's get a different number up there. So we've got 2 1/2 x minus 2 plus 3. I mentioned that I don't want you to just type this in Desmos, but that's somewhat partially true. I actually encourage you at some point in like the next 24 hours to at least type one of these in Desmos and check it. I'm talking mainly about your homework, but I'd like you to see what one of these look like on your computer. I hope you take a moment and do that. It's just that I don't want you to type it in and just kind of copy it down. I want you to think about it. Check your answer with Desmos. That actually would be a really good idea sometime in the next 24 hours. Okay, I hope that you start to, even though it's only the second problem, that you start to say, okay, you're kind of doing the same thing every time. Indeed I am. Okay, I'm going to start at 2. That's the A value, that's the number in front of the base. Okay, now when I start at 2, you'll notice that I'm marking it as like a star, because I just want to make sure you understand that it's probably not going to be where I stay, but it's a starting value. Now, from that starting value of 2 on the y-axis, I can start using shifting values, or shifting concepts. Remember that if you have a minus sign, it's always going to shift to the right. But if you have a plus sign at the end of the equation, that's actually going to be a vertical shift up. Now remember, this is always true. If I subtract, it's a shift to the right. But if I add to the end of any equation, it's a shift up. Okay, now it's not too hard to do that. All you have to do is go to the right 2 and go up 3. It's just a little bit of a counting game. So I go to the right 2 and I go up 3. And that gives me my final resting point. Now you do want to label this point carefully and correctly. Keep in mind that I went to the right 2, so that would actually put me at 2. But I went up 3 more. 3 more will take you to 5. That's the shifted starting value. Now, the y-intercept is kind of one of those things that you can always grab onto because, well, it's plug a 0 into the equation. You've heard that time and time again. If you plug a 0 into this equation, though, you've created a little bit of a monster. This would have been a good problem for me to put on the quiz. I didn't put a problem just like this on the quiz, but you had bits and pieces. So, what do you think? Basically, you have to be able to navigate the negative exponent. It's 2, 1/2 to the negative 2 plus 3. Let's navigate the negative exponent. And I hope I have good news for you. It's the same news we've always had. You can flip it. Now what you're going to flip is the base. If I flip the base, I get 2/1. Now the exponent is positive. See how that works? The negative exponent just flips the base. Now it's 2/1, which I hope you would say is really just 2 squared. It's really just 2 squared. Now, 2 squared is 4, and once I get to that point, I can see pretty quickly that it's going to come out to be 11. It's going to come out to be 11. Be careful. Notice I did the exponent first. You always do the exponent first. That way I can then get 4 times 2 and then plus 3 to eventually be 11. Now 11 is my y-intercept. 11 is my y-intercept. There's one more thing that we should mark on this graph. It's the asymptote. Maybe this idea is kind of new to you, but I've got good news because if the asymptote starts at 0, which it always does, if it starts at 0 and shifts up 3. Now think about this, an asymptote can shift up 3. So if that happens, I actually end up at 3. Now the reason this is good news is because the asymptote is always this outside number. Let me say that again, the asymptote is always this outside number. That's why everybody gets it right. As long as you kind of grab onto that, it will always be, well, in this case, it will be 3. Okay. I find that kids kind of, they have the most questions about this last number, and you'll notice I'm saving it till the end. 1/2. It's the base. Now, a screen ago shows you that the base is going to either tell you growth or decay. This base is less than 1. Since it's less than 1, it's got to be decay. Honestly, that's all you do with base. You just say, is it greater than or less than 1? And we know it's less than 1, so it's going to be decay. And so now we're ready to draw, well, a graph that I want you to get familiar with. It's called exponential decay. I know I've got a lot of things crisscrossing up here, but this graph right here, that would ultimately be the graph that's going to pass through this point. Okay, now I know I went a little slowly through the first two because again, trying to help you see that we do the same thing every time. Now instead of me giving you another problem saying, here, why don't you try it, what I've decided to do is I want to show you another problem it continues to have some slight variations, hoping that if I show you enough of these variations that you realize you can do the same thing every time. Okay, so I want to show you another one. Don't just be passive though. Try to be thinking with me, how can I do the same thing with 4e to the x minus 1? 4e to the x minus 1. It's that e that is supposed to be the slight variation. If you see that e, and you're kind of like, what is that? You know, maybe you've seen it before, but if you haven't, the letter e is actually just a special number. And everybody knows pi is about 3.14. Pi kind of takes the cake as the big math number, but e is honestly just as important. It's just that sometimes we don't get to it until this time of year. What is e? It's a number. It's a number. It's actually the natural number, so it has a name. It's the natural number. Basically because, as we'll look at a little bit, it shows up in nature. Okay? It shows up in nature. We'll talk about that a little more in about a week, but it's a number. It's about 2.71828. I know that just looks like a number to you guys, but it's really important. 2.71828. And because it's a number greater than 1, are you tracking with me here? It's a number greater than 1. It's still going to look like exponential growth. In fact, it is exponential growth. Sometimes we'll call it natural exponential growth because, again, it's that special number. Okay, now, there's a little more that I'll show you as the week goes on, but for now, it's enough information for us to do the same thing. At least that's the idea here. I want to try to draw a graph and kind of work this E into it. Are you already doing this? Are you saying, okay, I'll start at 4. I'll trust you, I'll start at 4. The number in front of the base is always the starting value. Bless you. Now you'll shift. Actually, down is the only shift in this problem, right? It's the only shift. Bless you. It's on the outside of the equation. So we shift down. Okay. Kind of a little bit almost too easy because if I start at 4 but shift down 1, then I guess I'm going to be at 3. I'm going to mark that as a point. Now maybe you note that that appears to be the Y-intercept. Well, it certainly does appear to be the Y-intercept, but let's go kind of do the 0 thing. If you do the 0 thing, it's e to the 0. Now, I know e is kind of new to you guys, but remember, anything to the 0, even lows to the 0, line to the 0, e to the 0 is 1. Now, I still have a 4 hanging out, so it's really 4 times 1. But, yep, you end up with 3. You end up with kind of what we already found. Now listen, in this case, my Y-intercept is the same as my shift point. Are you tracking here? This point actually is 2 points that we were finding a moment ago. All right, that's fine. That means that's kind of the only point that I'll be able to have on this graph. What graph? Well, a graph that has an asymptote. So remember, everybody gets the asymptote right, as long as you trust that or remember that the last number is always the asymptote. The only thing I've left to do is draw the correct graph. And we mentioned that the letter E is bigger than 1, so that means this is going to grow. You can honestly just draw a graph that's growing, just like all the rest of them. It's just a sketch. Now when it grows, it does go up very quickly, but when you go backwards, it's going to get close to that asymptote. I want to do one more thing with you. It's not just one more problem, it is one more idea, and that is when negatives show up. When negatives show up, yes, it makes the problem a little harder, no doubt. But, as I hope that you'll see, it simply creates a reflection. It creates a reflection. Okay, maybe you want to write down the word negatives. Maybe you just want to notice that there's a negative. There it is. It's -3. 4 to the x plus 1 plus 2. -3 for the x plus 1 plus 2. Hang in there with me. Because we're trying to have that same kind of approach. That is that I can do the same thing. I can do the same thing to this problem, even though there's a negative that we've done to the rest. And that is we can think about some points. We can think about some points. you trust me, then you would say, okay, -3 is the starting value, even though it's negative. All right, I'll start at -3. If I trust it, I'll believe it. If you trust it and believe it, you would say that +1 is a shift. It's a shift to the left. And go to left 1. Then I'll continue to shift. Now I'm going to shift up 2. I hope I'm not the only one who's thinking about this. In fact, I hope you're thinking about the value of this point. It's just a little counting game. You went left 1. You went up 2. Of course, you started down here. So you should be at -1, -1, -1, -1. It's a shift point. Let's do the Y-intercept. It's supposed to be the part that you kind of trained for. In other words, you have worked on some of this kind of exponent stuff. Now, if you plug a 0 in and you're trying to give your brain more of a workout, remember, without a calculator, you're going to think about -3 times 4 to the 1 plus 2. I know it's tempting to put it in a calculator, but you always do the exponents first. And when you think about it, it's just 4. 4 to the first power is just 4. I do the exponent first, I still have 4. And really, the rest of that's just a little arithmetic. So you can do it. You can get -10. -10 as your Y-intercept. I know it always works when the teacher does it, but I'm trying to get you to a point that you say it's going to be the same thing every time. We have a shift point, we have a Y-intercept. Now, I'm going to erase this shift point. I mean, it's up to you if you want to do that. I just don't want to have too much that we're looking at up here. Right now we have these 2 points. Everybody gets the asymptote correct? Remember, the asymptote starts at 0, which shifts up 2, so we can confidently say that we're going to be at 2. Again, everybody gets the asymptote, right? Now, if you put these 2 points in this asymptote down, you're going to get some credit. I'd love to see you, though, get full credit with the correct graph. Okay, now here's the new part. 4 would have been exponential growth. Are you with me? 4 would have been exponential growth. Now, if you picture exponential growth, you might be picturing something like this. You see, this graph, though, is going to be the reflection of that. Because when you have a negative sign in front of the equation, it's always a reflection. Specifically, it's a reflection over the x-axis. And here's the part where you have to take that dashed line that I drew, and you have to reflect it over the x-axis. You have to take it, you have to flip it down. Take that graph and flip it down. You're going to only end up with this graph. You're going to end up with this graph. So the graph that I drew is the reflection of, again, of our dotted line. I'm going to get rid of that dotted line because sometimes kids aren't sure if I need both. You don't need both. You really just need to find the answer. I would like to do one more reflection. I'm aware there's only a few minutes. You guys have been good sports. Trust me, this one is a lot faster. For a couple reasons. First of all, there's not much to it. And also, because we need to do it a little faster. So we've got 3 to the negative x. 3 to the negative x. Again, we will do this a little bit faster. Yes, we see a negative, but we also see, I hope that you see the number 3. Number 3 is the starting value. Well, it's also the final value. It's the final value because there's no shifting. So we have taken care of the Y-intercept and the shift point all in one step. We see the number 3, we see no shifting. Now the only other thing here, excuse me, there's still an asymptote. Forgive me, I almost forgot, there's still an asymptote. It always starts at y equals 0. It just stays at y equals 0 because there's no shifting. Okay, now you ready? The only other thing is to think about the base. Now the base of 2 would have said growth. Growth would have once again been this dashed line. However, we have a negative. This time the negative is on x. Whenever you have a negative on x, it's always a reflection over the y-axis. Be careful, that's like the new thing for this problem. It's a reflection over the y-axis. Now check this out. If you take this dashed line and you reflect it over the y-axis, you're going to fold it this way. If you fold it this way, it's now going to go this way. That graph looks familiar. That graph looks familiar. One last thing. A negative exponent, you've learned the last couple days, flips the base. Well, check this out. If I flip the base, I actually get a base of 1/2. 1/2 is decay. 1/2 is decay. It's exactly what we just drew. So sometimes kids will think of this as a reflection. Sometimes they'll think of it as decay. It's the same thing. And that's the other negative that you can throw into a problem. Okay. We look at the homework helper. As I said at the beginning of the lesson, let's have a good 2 weeks. Let's make sure that you keep learning. And the homework helper is one step in learning. And we will continue tomorrow.